My project is part of a program project grant, which is called Protect, and the co-directors are Kram El-Shawabke, a professor in civil engineering here at Northeastern University, and then Jose Cordero at the University of Puerto Rico. So that's kind of a background umbrella. One thing is I was careful to put my coffee down here. In a recent talk, the speaker spilled his coffee over his computer halfway through the lecture, so it was really exciting after that. So here's an outline of my presentation. Our stuff has a big impact. You can tell that because I'm wearing a tie. You don't usually wear a tie, but that shows you it's a big impact. We're in the field of mass spectrometry. That's the idea of mass tags. And the basic idea is we want to detect chemicals, especially trace chemicals, chemicals where the amounts are very small. So this is a chemical detection speech. So a little bit of background on mass spectrometry and then mass tags. Talk about application areas in general, and then the significance of small samples. And then talk about, we work on advanced mass tags, we call them. And then from the general application areas, I'll focus on 3 areas that we're working on. So the impact, the basic idea is early detection of things that are going well or going wrong in terms of looking at the chemicals involved. And early detection can be at the stage where you can really prevent some disease process. Early detection of disease is always important. Or in terms of treatment, is the treatment going well, and you find that out early in the game. And so that's the general impact of the technology. So if you know about a mass spectrometer, this will slay you. If you don't know anything, you'll learn nothing here. But at any rate, a mass spectrometer is sort of about as big as a refrigerator, and it's got a vacuum inside. And then the reason there's a vacuum in there is you got ions flying around under the influence of electric and magnetic fields, and you want to get them to the detector in a precise way, so you don't want them bouncing off of gas molecules en route. And so that's the reason for the vacuum. The molecules become ions in the so-called ion source, where some dose of energy, maybe it's photons or some voltage and small droplets, whatever, takes these chemicals of interest and converts them into ions. And then once they're ions and you got these electromagnetic fields, you can really zip them around very, very exactly. So the analogy here is these ducks flying. So my first prop, we'll put that up, and so there's an ion. So the problem with the mass spectrometer, and it's a very popular technology. It passed $2 billion market in about 2000. It's probably going about past $3 billion now. We've got 25 mass spectrometers on campus. There's a dirty sort of secret here, a problem everybody's aware of, and that is that analytes vary in their response. They just don't all fly that well, coming out of the ion source, in particular. And so what we have here is we have 4 kinds of ion sources. These are called electrospray. We can look at negative ions or positive ions, atmospheric pressure chemical ionization, negative, positive, and then down here as well. And we got 2 kinds of modern mass spectrometers. What we see here is we got a bunch of flavonoids. These are all structural analogs, and we see a wide variation in response. And that's very frustrating. And on the one hand, the mass spectrometer is so sensitive that you can detect these lower concentration analytes in an ordinary sample fine. But if you really want to do multi-analyte detection of trace chemicals, this is just hopeless. And this is not just running these things in one spectrum. This is taking every one of these compounds and tuning up conditions very carefully for every one of them, and then plotting this data. You say, well, I know how to fix this. We'll take this performer over here. Whoops. Previous, let's try that, okay. We'll take this compound here, this ion, and we'll make that a tag. We'll put that on the other ones that are not so sensitive. And then the idea is that that as a tag will take over the response. And that's what a mass tag is. You pick the best responders and you attach them to the ones that don't work so well. And then what you do, you don't just go with flavonoids for flavonoids. You pick the best mass tags of all and make those general mass tags. So that's the idea. You've got a situation where you got a trace amount of a chemical you want to detect, and so covalently you link some mass tags, so-called, to it. It gives a very strong response in the mass spectrometer, and then you got a strong signal. That's the basic idea. So the application areas in general, there are just a lot of areas where early detection can be of benefit. And as I mentioned, we're going to talk about 3 of these in a little bit more detail in terms of what we're doing. In small samples is very important in the health area. People are finding tumors earlier and earlier. They're smaller. Everybody wants a piece of it to do an analysis. And so if you want to really characterize, you're dealing with a small sample. Breath collection. There has to be an enormous amount more of medical information, health information in breath than we're sampling right now. So that's an opportunity, for example. Epidemiology samples, you got samples in the freezer, they're 30 years old, there's 5 milliliters of serum there. You want 1 milliliter of that serum because you got some idea that DDT caused breast cancer and the exposure was 20 years ago. Forget it. How about 100 microliters? Probably not. How about 10 microliters? Okay, now the committee will consider, letting you get some of that sample to test. So these are some areas where high sensitivity. So what we do is we design and build what we call advanced mass tags to give an extra boost in sensitivity and specificity. And we're not only interested in the sensitivity, we're interested in the multi-analyte detection. We want to take all these chemicals of interest and bring them up to a high sensitivity level. So it's a multi-analyte as well as this extra sensitivity and specificity. So here's an example of an advanced mass tag. We call this an intensified neutral loss tag. And so we have an analyte here, and so it doesn't have the sensitivity we want. So our tag can be represented like this. It goes after some functional groups, so we're after a class of analytes that share a common functional group. So we have this, we've made the derivative. And then during the mass spectrometry flight, what happens is we have a little cloud of gas that's placed in front of the ion coming along to give it some weak collisions. And this tag is very labile in the middle, and part of it falls off and the charge jumps to the other side, and under weak collision conditions. And what that does is, with specificity, it drops those ducks, in a sense, out of the ordinary flight pattern to get rid of more of the background noise. And so that's the idea of this intensified neutral loss tag. So I told my 8-year-old grandson about this, Connor, and he said, gee, you need a prop for that. I have just what you need. And so here's a prop for a mass tag that's going to a transformer jet fighter, okay? And so when this goes through the mass spectrometer, just a little gas zone there.